Hi there. Here's a quick peek at the answers. If you feel good about it, you can just move on. Otherwise, I'm going to explain how I got them. Here we go. Take a pause. Okay, I want to start by looking at the electron configurations. If you had trouble with that, it might be because tin is actually SN on the periodic table. So if you couldn't find tin, that might be why. It's stannous is its Latin name. So there's tin number 50. So to do its noble gas configuration, I take krypton, that's its base, that's its noble gas that's just before it, and I move on further from here. This is the 5th row, so I call this 5s2. It's 5 down, 5s2. And then I go to 4d10, that gets me through here. And then I'll end it with 5p2. So krypton, 5s2, 4d10, 5p2. Okay, now I'm going to take a moment and take a look at what's happening with the ion charges in this electron configuration. Remember, when you become an ion, you want to be able to have a noble gas configuration. That's key. I can see magnesium was able to do that. It took its 2 valence electrons and it lost them, and now it's like a noble gas. It's isoelectric to a noble gas configuration, which is what they're going for the whole time. That's following Hund's rule. Hund's rule again is the idea that when you form an ion, you want to have things that are filled, empty, or half filled. That would be the best way to go, the most stable way to go. So that's why these transition metals, they can't possibly get rid of all their electrons to maybe be empty or filled, but they can do the best they can. Take a look at zinc here. We have to remember that zinc is a 2+, and he could, 1, 2, and then 10, that's 12 total electrons. He can't possibly lose all 12 electrons to become like a noble gas. So he's got to do the best he can. He will lose these 2 electrons, which I can see here. He lost those 2. He lost those 2, at least he's got this guy filled, and the other guy empty. It's looking pretty good. According to Hund's rule, it's doing pretty good. Not perfect, but pretty good. Copper here does the best it can. It's got to be a 2+, so the 2 electrons it loses are these 4 s's. It's not super pretty, but at least it emptied out its 4. Then it's got its 3d9. That's not really filled. It's not empty. It's not half filled. It's kind of wonky filled, but it's the best it can do if it wants to be a 2+ charge. Titanium here, 2+, I can see that it lost its 4s. Now, if you think about it, if he has 2 to lose, he could lose these 3 Ds, or he could lose these 4 S's. So I'm kind of thinking to myself, every single time where they're losing the S kind of spots. So that must be the same pattern I'm going to follow down here with iron. It's going to be argon. It's going to lose these 4 S's. That's not there anymore, but that's only 2 electrons, so it must pick off one of these electrons too, to be 3d5. If I think about that, well, that seems pretty good because now I've emptied out the 4s and I have a half-filled D block. Half-filled means it has less electron repulsion. That's much more stable. According to Hund's rule, doing pretty good. So let's look at the tin. I'm going to become a 2+. The best way to do that would be to, well, I guess I'll remove this one. That's the best way to go. Krypton, 5s2, 4d10. In that way, I've got a full here, and I've emptied out my p's. That's a pretty good deal. Now I'm going to 4+. I'll get rid of my 5p2s. They're the most outer ones. They're the easiest to lose. And then I'll be losing my s block here. So I'll become krypton, 4d10. If you notice, what we're doing every single time is we're removing the outermost electron when you think of the energy level style. So in other words, when we write the electron configurations, we write d second. But that's not the outermost electron. The outermost electron will be the energy level that's the largest. And that actually happens to be in those s regions, or here these 5s. These are your outer energy levels, and those are the ones will be lost. So when an ion is made, which orbital is where the electrons are removed first? From the outermost energy level, the highest energy level that you have. It's not always the last thing that you write in your electron configuration. It's always going to be the outermost energy level. And why would you want to do that? Because according to Coulomb's law, which is KQQ over D, the K being a constant, the Q being the electron to the protons, those don't change. The only thing that's changing here is our distance. I want to remove the electrons that are the furthest away. The furthest away ones will be the highest principal energy levels. the highest energy level numbers. I want to bring this to something you've seen before, actually. Here's our PES. So let's think about this. Is krypton right here. Sorry. The picture on the right is krypton. And I've written in yellow on the bottom how we would normally write the electron configuration. We'd say 4s2, 3d10, 4p6. That's not really its proper shorthand electron configuration, but we're going to go with it here. So 4s2, 3d10, 4p6. So you can see the order that we would normally write it in, but that's not the order it goes in the PES. You can see it's more this style, where the outer energy level is actually at a higher energy level. I can see that by the PES. It does go, this has skipped over its 1. This is 2s2, 2p6, 3s2, 3p6, 3d10, 4s2, 4p6. We teach you to write it the way this yellow is because you'll never go wrong however you write it. You'll never go wrong in the order if you keep remembering it this way, the way we've always taught it. But remember, the PES really does rearrange itself. It rearranges itself at that scandium level. And we talked about this during our PES stuff. So if I did it for scandium, here's in yellow how I would teach you to write the electron configuration. You write it like that, you're good. But technically speaking, according to the order of energy levels of who has the most and least energy, the binding energy, this one here ends with 3d1 and 4s2. I'm not sure if you remember this picture, but this was one of those tricky ones on your PES part. So the electrons you're going to lose first are going to be the outermost energy electrons. The 4 is the outermost energy level. We'll lose those first. And according to the PES, those are the least strongly held. According to Coulomb's law, it's further away, it's easier to lose. Okay, so that brings me to the end of that.